Welcome to the design of concrete structure course. So in this lecture, today we are in lecture number 10. So up to this lecture number 9, we have derived the equations for doubly reinforced section, doubly reinforced beam. So till now we have discussed basics of beam, like starting from loads, then material properties, then we have discussed singly reinforced beam in details. And then in the last class, we have started the concept of doubly reinforced beam. So now at this point, I hope you guys have understood the what is doubly reinforced beam. So when we need to provide the doubly reinforced beam. So when the singly reinforced beam is not adequate to take the loads, that time we provide the doubly reinforced beam. For example, a beam, if it is, let me draw it here. So if it is a rectangular beam or any beam in that sense, so it will have certain B value. Similarly, it will have some certain D value. D is nothing but effective depth, the D. And in case of single reinforced section, reinforcements are provided only at the one side, that is at the bottom, if the section is at the midspan, right? So these bars are provided at the bottom. So now, what is the moment carrying capacity of this section? Mu lim. If you recall, we have discussed in the singly reinforced section also. So mu lim for this section will be 0.36 fck. So basically, b something bd square or something more terms are there. So it is nothing but uh, concrete force c into lever arm is the lever arm l will nothing but it will give you the mu lim. So so this is the lever arm, right? So from here to where the concrete net c is acting, so that distance is lever arm. So now in a single reinforced section, this value mu lim depends how to increase the mu lim. Okay, so if, for example, suddenly load has increased on a beam, or more UDL, more intensity of UDL is acting on a beam. So in that case, we have to increase our mu lim in our structure. So now, how to increase the mu lim? What are the options we have? So in single reinforced section, if you increase the value of B or D, then we can increase mu lim, right? B and D both are multiplications. So if both the values are increases, or either anyone is increases, so then mu lim will be increased, right? This is one option to do that. So now, if you see in reality, all the structures, the depth of the beam also is limited. Like we cannot increase the depth of the beam as we possible, because more deep beams may not be looking aesthetically good. So based on architectural design, they will give us what could be the depth of the beam, what could be the width of the beam. Again, width of the beam also depends on the width of the wall. So if whatever maybe the wall thickness, so similar thing we provided as a beam thickness, right? So BND also has a limitation. We cannot increase BND arbitrarily at any point. So that's why the increase in BND is also a not good option. So what is the next alternative we have? So next alternative we have is we can provide the reinforcement of the steel at the compression side also, because concrete cannot take much tension force, whereas steel is very good in the sense it can take equal amount of tension as well as equal amount of compression also. So we can add additional reinforcement at the compression side, like here. Additional reinforcements we can provide to increase the moment capacity C. So as we added additional reinforcement at the compression side, we have to add additional reinforcement at the in the tension side also, because the net moment or our section should be in equilibrium. Means whatever total compression force is there, same amount should be total tension force. That is the balance section, or that is our section we have to design it. So that's what we discussed in the last class in details. The theory part of doubly reinforced beam. So now in this class we'll be solving an example of from basic scratch how to solve the beam in the doubly reinforced beam. So let's get started. So the question here is design a simply supported beam of a effective span of 8 meter subjected to imposed load of 35 kilonewton per meter. The beam dimension and other data are given to us. See, B already given to us. B value normally what? Width of the beam. So width of the beam normally depends on the architectural aspect. Means what is the width of the wall, or all these things comes from width of the B. That is B. And what is D? D is the capital overall depth, right? Capital D is overall depth of the beam. That is also given to us 700. So these two values are fixed. and we have to use M20 concrete and Fe415 grade of steel. So these are the data are available to us. We have to design a simply supported beam. So what do you mean by design? Design means we have to find out how many reinforcements are there. Anyway, B and D, those both the values are given to us, right? So if I draw, the section will already is given to us. So if it is a rectangular section, okay, so B and D, B is this much width, which is given to us, that is 300 mm, and similarly D is overall depth, capital D is given to us, that is also 700 mm. And what else given? M20 grade of concrete we have to use, and Fe 415 grade of steel also we have to use. Okay, so that is the data given to us. We have to find it out over the we have to design the section. Design in the sense we have to find it out what is the how many reinforcements are required at the bottom and what is the reinforcement at the top. Then I know what is the spacing. All these things we have to specify in this problem. Okay, so now first is dead load calculation, because dead load first step is what? So we have discussed in the last class also. First calculation is dead load calculation. So what is dead load? So dead load is the load of the structure itself, right? In the question it is given imposed load of 35 kilonewton per meter. That means extra load is acting on the structure, that is 35 kilonewton per meter, right? So that is imposed load. Live load is acting. So in the question live load is given to us 35 kilonewton per meter. But the beam has its own weight, right? That we call it dead load of the beam. So dead load of the beam also has to be computed first, because that weight of the beam also is acting on this, on this beam. So how much is the dead load? So dead load can be easily computed. So B and D is given to us. So B and D is 300 and capital D is 600, right? So what is the cross sectional area then? So cross sectional area will be, B into D. So B is 0.3, if you convert it into a meter, 0.3, and D also if you convert it into a meter, 0.7. So this is the cross sectional area multiplied by unit weight of concrete. So unit weight of concrete, we know it is 25 kilonewton per meter cube. That is also given in our IS code IS 456. Earlier also we have used the same value. Okay, so now if you multiply it, cross sectional area with the unit weight, we will get the dead load. So dead load is 5.25 kilonewton per meter. Dead load is acting. And imposed load means this load is already given to us, that is 35 kilonewton per meter. So now what is the total load acting on a structure? So total load acting on a structure, this plus this, right? Dead load plus live load, which will give you 40.25 kilonewton per meter is the total load acting. So now we know how much load is acting. So in the question it is given that it is simply supported beam. So simply supported beam means, let me draw it here. So this is a beam, and simply supported means both the ends are simply supporting. Okay, and this is the total length. Total length is L, effective L also given to us 8 meter, right? And the UDL is active. Total load. So total load is nothing but 40.25 UDL is acting here in this beam. So what is the bending moment diagram of this beam? So bending moment diagram, if you draw, it will be something like that, parabolic. We have discussed in details earlier classes also. And bending moment will be maximum at the center. And what is this value? So this already we know it is WL square by 8, right? So this is the maximum bending moment will occur at the center. So if you design a beam, if you design this beam by considering the bending moment is maximum at the center, then if our beam can take maximum bending moment, then our beam can take, other bending moments are less than the maximum one, right? So if you design a beam by considering this is the bending moment, then for the other sections also our beam will be safe, because in other section bending moment are less. Okay, so that's why always we take the maximum bending moment, how much is acting on a beam, and that we consider it. So what will happen here? So WL square by 8, so that is the maximum bending moment we have to compute. So now factored bending moment is, WL square by 8. So this is the formula already we derived also earlier classes. So WL square by 8 multiplied by 1.5. So what is 1.5? 1.5 is the partial safety factor. Partial safety factor as per IS code, as I mentioned. So we have to increase the load by 1.5 times, right? So that's why partial safety factor 1.5 times multiplied by W is 40.25 into L square. L is given to us, effective length is 8 meter. So 8 into 8 divided by 8. So whatever you get it, that is a 482.96 kilonewton meter. So that much bending moment is acting on the center of the beam. So we have to design the beam which should take that much bending moment. So the resistance moment of this beam should be at least this much. So ideally it should be more than this much, right? But at least minimum bending moment, effective bending moment, or the mu limb should be this much, right? I mean, not mu limb, basically the resistance moment should be at least 482.96 kilonewton meter. Okay, so now that much bending moment, maximum bending moment, now we got it. So our next step is now to find it out the cross section, right? Cross section of the beam. So already we have given, so this is the W reinforced section, right? So that structure will be there. So in the W reinforced section, we provide reinforcement at the top also, right? So this is the top reinforcement. And from top fiber to center the CG of these three bars, or whatever is the number of bars, that we call it D dash, small D dash. So okay, so that value, let's assume that D dash value is 70 mm. So normally total length is what, 700 mm. Normally it is 10% of the total span. We can assume, maybe others can assume 60 mm, others can assume 50 mm. So any values are fine, maybe as long as your values are reasonable, it is fine. So d dash value you assume 70 mm. Then what is the small d then? Small d will be 700 minus 7d. So 680. So these are also initial guesses. It is also not final value. We'll assume these values and then we'll check it. If it is fine, then our problem is solved. If it is not adequate, then we have to redesign. We have to change the values. So this is our initial assumption. So small d value is 630. So you can assume maybe small d value also as the 620 or something, because here also at the bottom we have the clear cover, right? Clear cover also we can assume 50 mm. Then d value will be minus 50 also. Then it's 570 mm. So you can assume that also. No problem. So now let's see here in this problem. Let's assume d dash value is 70 and d value is small d value is this one. So now xu max by d. If you recall, we have discussed in the singly reinforced section also in details. Xu max by d for the Fe415 grade of steel, this Xu max by D value is how much? 0.48. Okay, so as I mentioned earlier also, how we derive this expression I have explained in details earlier lectures. Okay, so Xu max by D. Xu max means depth of the neutral axis by D, and this value should not maximum for the singly reinforced section. This value should not be more than 0.48. Okay, so now D value we assume something 630. Then XU max value also we got it 302 mm. So with 0.4 mm. So what is XU max? XU max is the depth of the neutral axis. So for example, here is the depth of the neutral axis. So this depth we call it XU max. So depth of the neutral axis. Okay. So that value we got it 302.4 mm is the depth of the neutral axis. So our initial assumption is we assume d dash value is 70 mm and d value is this much, and the xu make the depth of the neutral axis also we got it something like 302.4 mm. So now our first step one is determination of mu limb and ast limb. So as I mentioned in the earlier classes also, W reinforcement section can be divided into two parts. Okay, so let me draw it here. So, so this is the singly reinforced section which we discussed earlier classes. Okay, so singly reinforced section has a limitation, means mu will be mu limb. Okay, mu limb. So this section, singly reinforced section, section 1, this section can generate maximum of mu limb. Okay, but our how much moment is acting? Moment something 482 kilonewton mm, right? That much moment is acting on our beam, on our this example. So singly reinforced section has a limitation because moment cannot increase more than mu limb. Okay, so in that case, mu limb is there, plus we have to add additional reinforcement for the doubly reinforced case, right? So compression reinforcement as well as tension reinforcement we have to provide it, and then we get it our doubly reinforced section. So this is equal to our doubly reinforced section. So in the singly reinforced section, the concrete is there everywhere, right? Here concrete is there, whereas in the doubly, whereas in this section there is no concrete, only steel. Okay, and this is our main net W reinforced section where reinforcements are there and both sides, and this is the concrete part. Okay, so mu limb will get it from the singly reinforced section, and then we have to find it out mu2. If you recall, mu2 we have discussed the last classes, right? This is mu limb we call it, and this is mu2, and this is our final mu. So mu will be mu limb which is because of singly reinforced section mu limb plus mu2. Mu2 means because of this section. Okay, so now that is the concept of doubly reinforced section we discussed earlier. Okay, so now here in step 1, first we determine what is mu limb. Mu limb means because of this singly reinforced section, how much moment has generated, or the resisting moment, how much has generated. We have to, the how much moment is acting on a beam, that is 482 kilonewton meter moment is acting. So first let me check how much moment this singly reinforced section can generate. So what is the formula mu limb? We have discussed earlier also in the last classes how to this formula we have derived also. So this is basically concrete force 0.36 FCK BD something like that multiplied by the lever arm. Lever arm is 0.42 XU. XU minus 0.4 sorry D minus 0.42 XU is the lever arm, right? Then mu limb, if we substitute all the values, XU max is the last line only we have derived it. So XU by D value is 0.48. Okay, then B value is something 300 and D value is 630, right? Mm squared. So FCK is 20, and if you convert it into kilonewton meter, that's why we are multiplying it 10 to the power minus 6, and this is the moment mu limb. So now you can see that mu limb has generated 328.55. So this section can maximum withstand that much moment, 328.55 mm. But how much load is acting, or how much moment is acting on the beam? That is 482 kilonewton meter, right? So the moment is very high. Whereas if you determine only singly reinforced section, if you provide only singly reinforced section, then singly reinforced section can take maximum of 328.55 newton kilonewton meter. But the applied moment is very high, right? 482. So now the remaining part means 482 minus 328. So the extra 150, I mean, extra 150 kilonewton meter has to be taken care by the doubly reinforced section. Okay, so if you can draw only singly reinforced section, then singly reinforced section can take maximum of this much moment, right? But the applied moment is C 482, very high. That's why we have to provide additional reinforcements in this section. That's why we need doubly reinforced section. Now you understood. Anyway, so the mu limb we computed 382.55. Now what is AST? AST limb means in the singly reinforced section how much reinforcement we provided. AST limb. That also we compute. We know this formula. Mu limb by this 0.87 Fy is the steel force multiplied by the lever arm. This is D minus 0.42 XU. So we know this formula we have used earlier also for computing AST limb. And if you substitute mu limb by AST limb, so AST1 means reinforcement in the singly reinforced section, AST1. That value should be comes out to 1809.14 mm squared. So now we know all the parameters of singly reinforced section. That is our step 1, means determination of mu limb, already we computed it, and AST limb. AST limb is this much. Okay, area of steel in tension, limiting value means maximum in singly reinforced section is this much we can provide it. Okay, so now our step 1 is over. Now we are into step 2. In the step 2 means we have to find out mu2 AC, area of steel. So let me draw it again here. So the same section earlier, whatever we have drawn. So now we have to find out mu2. Mu2 is because of only additional compression reinforcement and tension reinforcement. So compression reinforcement at the provided at the top and tension reinforcement at the bottom, right? So now this is only second part I am drawing here. So this is mu2 that we are finding out in this section now, mu2. So how to find it out mu2? That also we discussed in the last theory classes, last lecture number that's 10. Before that, this lecture we have theory part we have discussed. So mu2 means how much moment has generated here. So total moment acting on this beam is 482.96, right? That much total moment is acting on our beam. But because of singly reinforced section, how much it can take? Singly reinforced section can take 328.55. Now the remaining part means 482 minus 380, it means 154 Newton per Newton mm square. That much moment has to be taken care by the doubly reinforced section, right? So this additional part has to be taken care by this part, and this we call it mu2, right? That's what we discussed in the last slide. Also, I have drawn it here. So this mu2 value should be 150. Minimum should be 154.41 kilonewton meter, right? So mu2 means how much resisting moment is there, that now we computed 154.41. So now find out what is d dash by d ratio. So d dash by d ratio is 70, by d dash is 70 and d is 630, so this is 0.11. Okay, now we are finding out what is the compression force in the compression steel. What is the net compression force in this compression steel? So how to find it out? See C2 here. So how to find it out? C2, C2. So compression force is nothing but what? Force into force will be stress into cross-sectional area, right? So how much stress is acting in this level? How much compressive stress is acting in this level? That we have to find it out. This multiplied by a that cross-sectional area ASC will give you the total will give you the total compressive force C2, right? So for that, first you have to find out how much stress is acting here at this point. That stress we call it FSC. Okay, FSC is for stresses in steel, compression steel. So S means steel and C means compression. So forces or stresses in the compression steel, how much it is? That is FSC. So now we are computing what is the stresses at this point. So how to do that? So the top fiber is subjected to compression, right? And bottom fiber is subject to tension. That we know. So now top fiber, what is the stress at the top fiber? So the top fiber already we know the stress at this point is 0.0035, right? Maximum stresses in the concrete. Now what will be the stress at this point? So we have to do the interpolation that's from the strain diagram. If you recall, we have discussed in the last classes also. We have to draw the strain diagram here. So something like that will be the strain diagram, right? So at this level, at this concrete level, what is the stress here? What is the strain here? That we have to compute. And this last extreme stress we know it's 0.00035, something is there, right? So this extreme strain we know. Now this strain, because we are finding out what is the strain at this level, concrete level, that strain we can easily compute from the strain diagram. So once we know the strain in a concrete, now from the stress strain curve of concrete, we can find it out how much stress is there on this beam, or that can be tabulated. So in the last slide, last lecture, we have discussed this table. Okay, using d dash by d value, how we can interpolate what is the stress acting on this concrete, acting on this compression steel. So based on d dash by d ratio, we have drawn this table in the last class. We have computed all the values. So here in this problem, d dash by d value is 0.11. So in this table, find it out what is 0, where is 0.11. So in this table, we have 0.01 and 0.15, right? But our value is 0.11. So we have to interpolate. We have to take this value, and then we have to interpolate it for the 0.11. So anyway, so it will be very similar to, so our value 0.11 is actually middle of these two span, right? 0.1 and 0.15. So we have to interpolate between these 2 points. So FSC, so we are using Fe415 grade of steel, right? So 415 corresponding to that, what is the stress? C 353 and 342. For d dash by d value 0.1, the FSC value is 353, and d dash by d value 0.15, the value is 342, right? Our value is 0.11, so in this middle range, so we have to interpolate it. So FSC equal to 353 minus 350 minus 342 by 5, right? Total division is 5. So that will give you how much net stress is acting on this compression fiber. So which is nothing but 350 Newton per mm square. So FSC means stresses on a compressive steel in this point. At this point, that value is 350.8 Newton mm square. From this table we got it. So while solving the problem, this table you can keep it along with you. You can easily interpolate the data. So you can imagine also, right? This is for 0.1, this value is 353, but in our problem how much it is? It is 0.11, little extra, little more, right? So whatever we got it, that is also near to 3.53. It is 3.50.8, right? Based on interpolation we got it this value. So now FSC value has been computed. Now what will be the ASC? ASC means area of steel in compression. So this value, what is the steel, percentage of steel here? ASC, total amount of steel, ASC, which will be how much moment divided by the force, right? So moment mu2 is what? Moment is force into distance, right? So force is how much? Force is stresses multiplied by ASC. Okay, so this is the stresses multiplied by ASC, area of compression steel, into lever arm. Lever arm is d dash by d, right? This distance is lever arm. That will give you mu2, right? So from this expression we can easily compute what is the value of ASC. So ASC is mu2 already we know 154.41, into 10 to the power 6 because we are converting kilonewton into Newton mm. Then divided by FSC minus FCC. FSC is 350.8 minus FCC. FCC means that what is the stresses on a concrete. So that is also because we are using M20, right? And at this point, what is the stress? So 0.446, if you multiply it, so you will get total value, and D capital D small d value is 630 we know, and D dash value is 70, and then we got it, what is the value of ASC. Okay, so ASC now we got it. So now you can ask from where we got it 0.446. So 0.446 means what is the maximum stress at the top fiber. So top fiber is maximum stress is 0.446 FCK, right? If you recall the stress strain curve of concrete, stress strain curve of concrete was something like that, right? As per IS code. So what is this maximum value? Maximum value is 0.446 FCK, right? So same thing value is written here, 0.446 FCK. So here FCK is 20. And now substitute all the values, you will get ASC is 806.515. So this is ASC. Now we have to compute what is AST. AST2. This portion. AST2. So AST2 how will compute? So this section should be in equilibrium, right? So net compression total C2 equal to total T2, right? Total compression force generated in this section equal to total tension force. So based on this equilibrium equation, this AS2 can be calculated. So all these equations we have derived in the last class. Okay, so please refer last lecture to get cleared how do we get this formula. So this is something, but so total compression force is how much? Total compression force will be stresses. Stresses is this much into cross sectional area will be the force, right? So this is total compression force equal to total tension force. So total tension force is tension stress is 0.87 Fy. This multiplied by AST2 will give you total tension force. So now from this expression we can find out what is AST2. So just plug in all the values, you will get it. AST2 value is this much. Now total, what is total AST? Total AST will be AST1, which is discussed in the last slide. In the step 1 we computed AST1, and this AST2 just now we computed 763, and if you add both you will get total AST. So area of tension steel is 250.2572 mm square, whereas total compression steel is 806.52 51 mm square. So now we computed the total tension steel, total compression steel, both we computed. So now in the step 3 is check for the minimum and maximum tension steel and compression steel. So as we discussed in the last lecture also, our code has specified the minimum and maximum tension and compression steel. So in no case we should not provide more reinforcement whatever specified in the IS code. So in compression, what is there in compression? Minimum we have to provide it 0.2%. That's what we discussed in the last lecture also. Please refer that lecture. So minimum in compression we should provide minimum of 0.2%, right? So minimum of 0.2% is B into D. So 0.2 into B into D by 100, right? So this is coming by 420 mm. So minimum compression reinforcement we have to provide it is 420 mm. And what is maximum reinforcement we have to provide it? That is the 4% of the total cross-sectional area. That is as per our IS code, right? In our IS code said in no case we should not provide compression reinforcement more than 4% of the cross-sectional area of the beam. So cross-sectional area is B into D 300 into 700 and 4%. So 4 by 100, which is 8400. So whatever compression reinforcement we have provided in the last slide, that should be in this range. It should be more than 420 and less than 8400. How much we provided? We provided 806, right? Last slide, if you see, we got it. ASC value is 806.51 mm square, which is in this range, right? It is more than 420, less than 840. So hence it is okay. We have to check it. If this value comes less than this value, less than 420 value, then we should provide at least minimum one of 420. And if this value comes more than 8400, means maximum one, then again we have to redesign the section. But in our case it is in middle, so our hence it is okay. So as per our code it is fine. That is in compression. Now in tension also our code said with this formula we have to find it out what is the minimum reinforcement you have to provide. The 0.85 B into D by Fy. So if you plug in all the values you will get it 387.1. So minimum we have to provide is 387.1 tension reinforcement. and maximum is again 4% of the total cross-sectional area, which is nothing but 8400. So whatever we provided in the last slide, we covered got it. AST value is 2572, which is more than 357 and less than 8400. So hence again it is also okay. So we have checked it. So like that, whenever you design it, so in the step 3, always you have to check it, whatever reinforcement we got it, whether it is in the limit or not as per our IS code. So that's why we call it in this method also limit state method, right? So see that we are limiting all the reinforcement. The reinforcement should not be more than this value, should not be more than 8400, and less, no, not should not be less than this value, right? That's why we are limiting all these parameters. That's why the method also called limit, limit state method of design philosophy. So step 3 is also over. So now in the last step, that is step 4, is now we have to draw the cross section. So ASC value, now we know we have to provide it something like 850. So we can provide it two 20 mm bar and two 12 mm bar. You can use any other combination. We can make it uniform, and you can use any other combination for that also. So in that case, you can provide maybe four or six 12 mm bar also. You can compute what is the net value. If you provide two 20 mm bar and two 12 mm bar, then how much cross sectional area you got it? That is 628. So how much we got it? So this is pi by 4 into d square, right? How we compute? If you provide 220 mm bar means what is the cross sectional area we provided? So pi by 4. So pi by 4, let me write it here. So pi by 4 into 20 square, right? This is for one reinforcement, right? So we are providing 220 mm bar. So this plus pi by 4 again into 12 square, right? 212 mm square, so multiplied by again 2. So if you do all this computation, you will get it 854 mm square. Okay, so whatever we need maybe 850 mm square. We provided 854 mm square, so it is okay. Similarly, AST value also, AST value you have to provide something 2450 or something we need to provide. Here we provided 4 numbers of 25 mm tor bar and 2 numbers of 20 mm tor bar. Like that we have to specify, and we have to draw the cross section. Okay, and that if you could add it, you will get near to 2500. Always you have to provide whatever we got it near to that value, and more than this small quantity of more should be there. Then you would draw the cross section. D will already given to us 700, B will also given to us 300, and we are providing 4 bars, right? 220 mm and 212 mm. So that's why 4 bars are provided. That is our ASC value, and at the bottom we are providing 6 bars. So out of 6, 425 mm and 220 mm bar, 6 bars we are providing. So here also you see at the bottom we have to draw it, and this is our final design of the reinforcement. So now this design will be given to the site engineer. Now he will make the beam as per the drawing, and he will execute it on the site. So that's how the doubly reinforcement design happens. So we have done this problem from basic scratch, and ultimately we have drawn the doubly reinforced section. So this completes our doubly reinforced section. Now I think you have understand a proper understanding of how to design the singly reinforced section and how to design the doubly reinforced section, and in which case we have to provide the singly reinforced section, again which case you have to provide the doubly reinforced section. All these parameters now you have understood. So in the next class onwards, we will be starting the slab design. Thank you.